Have you ever wondered why some welds crack, while others hold for decades? Or why two metals that look the same can behave completely differently under the torch? The answer lies in metallurgy, the science behind the metal. In this video, we're going to break down the metallurgy basics every welder needs to know. Let's get into it. Metallurgy is the science of metals, how they're structured, how they behave, and how they change under heat and pressure. In welding, metallurgy is what determines whether your joint will be strong, ductile, and crack-free, or weak, brittle, and prone to failure. Metals are made up of tiny crystals called grains. The size and arrangement of these grains directly affects the metal's strength and toughness. When you heat a metal during welding, you are actually changing this grain structure, and knowing what happens next is everything. One of the most critical concepts in welding metallurgy is the heat-affected zone, or HAZ. This is the area of the base metal that wasn't melted, but was still heated enough to change its properties. In the HAZ, you'll find three things happening: grain growth, grains get larger, reducing toughness; hardening or softening, depending on the alloy; residual stresses, internal stresses left behind as the metal cools. For example, in high-strength steels, the HAZ can become extremely hard and brittle, creating a perfect environment for hydrogen cracking. This is why preheating and controlled cooling are not optional, they're essential. Not all steels are equally easy to weld. The key factor is carbon content. Carbon makes steel harder, but it also makes it more difficult to weld without cracking. We use a formula called the carbon equivalent, CE, to judge a steel's weldability. Carbon equivalent equals carbon plus manganese divided by 6, plus chromium plus molybdenum plus vanadium divided by 5, plus nickel plus copper divided by 15. The higher the CE, the more care you need: preheating, post-weld heat treatment, low hydrogen electrodes, and controlled cooling. CE below 0.40 generally weldable without preheat. CE 0.04 to 0.60 preheating recommended. CE above 0.60 requires special procedures. This is why mild steel welds easily, but tool steels and high-carbon steels demand a lot more respect. Here's where it gets really interesting. Steel doesn't stay the same structure as it heats and cools, it actually transforms through different phases. At room temperature, most steel exists as ferrite and perlite, relatively soft and ductile. As it heats above 723 degrees Celsius, it transforms into austenite, a face-centered cubic structure that can absorb more carbon. Now here's the critical part: when steel cools slowly, it returns to ferrite and perlite, safe and tough. But if it cools too fast, the austenite transforms into martensite, an extremely hard, brittle structure that is the first cause of cold cracking in welds. Controlling your cooling rate is how you control whether you get tough ferrite or brittle martensite. Preheating slows the cooling rate. Interpass temperature control keeps it consistent. Post-weld heat treatment tempers the martensite to restore toughness. When metallurgy goes wrong, defects appear. The most common metallurgy-related weld defects are: first, hot cracking, solidification cracking, happens in the weld metal while it's still solidifying. Caused by low melting point impurities like sulfur and phosphorus. Solution: use filler metals with higher manganese-silicon ratios. Though cold cracking, hydrogen-induced cracking, occurs hours or days after welding. Caused by hydrogen trapped in the HAZ combined with a hard martensitic structure. Solution: low hydrogen electrodes, preheat, and slow cooling. Third, lamellar tearing, occurs in thick plates with inclusions running parallel to the surface. The through-thickness stress tears the metal apart. Solution: use low-sulfur steels and change joint design. Understanding the root metallurgical cause of a defect is the only way to truly eliminate it, not just patch it. So how do you apply all of this on the shop floor? Here are the 5 golden metallurgy rules every welder should follow. Rule 1: know your base metal. Always identify the steel grade and calculate or look up its carbon equivalent before welding. Rule 2: preheat when in doubt. For CE above 0.40, preheat to at least 100 to 200 degrees C. It dramatically reduces the risk of cracking. Rule 3: use low hydrogen consumables. For anything high strength, A7018 equivalent low hydrogen electrodes are your best friend. Rule 4: control heat input. Too much heat equals big HAZ and grain growth. Too little equals fast cooling and martensite. Find the balance. Rule 5. Post-weld heat treat when required. PWHT tempers martensite, relieves residual stresses, and restores toughness. It's not optional for critical applications. Metallurgy isn't just for engineers in labs, it's the foundation of every weld you make. Understanding what's happening inside the metal gives you the power to make decisions that separate a good welder from a great one. If you found this video helpful, smash that like button and subscribe for more welding science content. Drop your questions in the comments below, I read every single one. Next week, we're going deep on weld procedure specifications, WPS, don't miss it. See you then.